you can still keep adding to the chat where you are and what you're interested in with this, but I want to get started. Firstly, thank you everyone for showing up and registering for this. This is again a continuation of the Physics and Astronomy Sea Change webinars we've been doing to highlight some really cool practices people might think about doing in their physics and astronomy classrooms. I'm Alexis Knob. I am the project manager for that project, and you might have seen me through other things within AAPT or APS. And I'm really excited to hand things over to our speakers, Eric Kuo and Muxin Zhang, to talk about exciting things that are going on at University of Illinois Urbana-Champaign. If you have any questions, please put them in the chat or Q&A, and we'll get to them once that part of the talk begins. Anyway, thank you so much, and I'm handing it over.
Okay, thanks, Alexis. Well, it's good to see you all, and by that I mean, of course, see the list of attendees' names. But we're excited to share some work that we've been doing recently that builds on a long history of work about how we can build support for students here at the University of Illinois in terms of redesigning what's going on in the course. So we don't just mean like in terms of teaching or in terms of course activities, but we also mean in terms of other structures of the course, like policies and other infrastructural things. I'll talk about this later. We've done sort of the everything but the kitchen sink approach. And so I'm going to mention a lot of things in brief and sort of how we implement them and what we think we get out of them. And so if people want to follow up on those things, we're happy to talk more about that. But yes, we are Eric Kuo, that's me, Muxin Zhang is here also. We're at the University of Illinois, and to motivate what we're going to talk about, the thing that I want to point to is here. So at Illinois, physics is in the College of Engineering, right? And so like many physics departments, most of the students that come through our building are actually engineering students, right? So a lot of what motivates our work is the challenges that students might experience at the start of an engineering degree. And so specifically at the University of Illinois, about 74% of students who intend to major in engineering at the start of college graduate with an engineering degree. And actually 10% leave from when they enter to the time that as the end of Physics 1. And so for us, we call it Physics 211. I'll just mention that because I end up saying that a lot. But we're, of course, really concerned with that first semester or first 2 semesters where students are not just starting their engineering degree, they're starting college and they're learning about what it means to be an engineering student here. And so we also care about why students switch out of engineering. And so there's a lot of research on this, but I'm just taking one summary analysis that looked at 50 studies, factors related to leaving engineering. And so what they found broadly is inadequate teaching or advising is a contributor. The individualistic culture of engineering, students' low grades and their conceptual difficulties, students' low self-efficacy or self-confidence in their ability to complete an engineering degree. Students might have low or weak high school preparation. Engineering may not align with their interests and career goals, and that interest may wane because maybe taking engineering courses in your first year, they're not what you imagine being an engineer would be. And of course, this meta-analysis points to race and gender in a couple of ways. So one is that all of these other factors they find correlated with race and gender. They also find explicit things like sexism being factors why students switch out of engineering, right? But overall, this is our motivation to try to change course activities, policies, and infrastructure, right? And we really focus on this because we have a lot of students and not a lot of teachers. And so a lot of the ways that we affect students are just by affecting the trajectory that they're going through, right? And so this is in contrast to, you might have heard, there's a recent focus on social psychological interventions. And so these are commonly related to students' beliefs, or other factors that are related to academic success, like students' sense of belonging in, say, engineering, their sense of self-efficacy, their mindset, do they have a growth mindset or a fixed mindset, mindfulness, their perception of the utility value of a course, etc. Right? And a lot of these interventions that are developed primarily in psychology or psychology-related fields, they're interventions to target students' beliefs through discussion or reflection or telling. You might tell students, we want you to have a growth mindset, right? It's good to have a growth mindset because. So in contrast, our work is really focusing on changing how students experience the course by changing the structure of the course. So of course, we would like students to have a high sense of belonging, high self-efficacy, things like that. But the way that we're trying to impact those also involves changing what students actually do in the course. Okay, so introductory physics at the University of Illinois, our physics 1 is called Physics 211. It's calc-based mechanics. It's an early core requirement in every engineering major and many other STEM majors, and that's who takes that course. So the main thing that the physics department here has done to try to provide infrastructural support for students is we created a preparatory course for Physics 211. It's called Physics 100. And you get recommended to take Physics 100 if you score a certain score or below on the physics placement test. So when you come in intending to major in engineering here, you take a lot of placement tests for math and for physics. And so based on your physics placement test score, you might get recommended, but not required to take Physics 100. Okay, just to give you a sense of the scale here, in the fall, our Physics 211 is 650 students. In the spring, it's 1,200 students. That's sort of the on-sequence time to take it, because usually in that first semester, fall, students are taking calculus, which is a prerequisite for our Physics 211. Okay. So Physics 100, it's only taught in the fall, and it's typically about 400 students, right? And so these are students who are going to take Physics 100 in the fall, and they're going to, in the spring, move to Physics 211. Okay. Okay, so in terms of creating infrastructure for student success, if we have one recommendation of what's been successful, it is to create a whole preparatory course. Because once you do this, the department is committing an explicit structure to supporting students, right? It's an explicit piece of creating a pathway for success in engineering for students with less or weak high school preparation. The other thing about Physics 100 is that it's been in active development here for over 20 years, right? And so over time, Physics 100 has changed a lot. They've tried a lot of things. And so its current form is sort of also the historical development of the course. Okay. Okay, so this is the time when people usually have in their mind, does Physics 100 work? And so for a lot of people, that means, does it help students get their engineering degree? Unfortunately, there's no definitive answer. And it's because, we've created one small course during a student's whole college engineering experience. So it's hard to understand how this has an impact on that. You might ask a smaller question, does Physics 100 improve your Physics 211 grade? The answer there is year-by-year results are inconsistent. Sometimes you see a positive effect, but sometimes you see zero effect. And so it's complicated. One of the complications of this challenging analysis is there's no control group, right? So you have to really understand why you think Physics 100 will help, who you think it will help, and you'll try to understand differences between students who take Physics 100 and students who don't. The other thing is some of the proposed benefits are hard to detect. So for instance, we believe that Physics 100 helps students even get into Physics 211. And so it's hard to use the question, does it improve their 211 grade, as a way to understand the impact, because we think that some of what's happening is students might not even make it to 211 without Physics 100, right? And it's really hard to actually understand whether or not that's happening and whether or not that's helping. At the University of Illinois, also, Physics 100, the engineering population, and what it means to be an engineering student has changed a lot over time, a lot over the last 20 years that Physics 100 has existed, right? And so at the same time, Physics 100 isn't even playing a consistent role if it stays the same. Okay, so the question that I feel better about answering is, does Physics 100 allow us to structurally attend to known challenges with being an engineering student? This, I think the answer is yes. So one reason is it provides a structure for us to focus our efforts. Suddenly we can use Physics 100 as a place to provide support for students and as a place to improve how we support students, right? One good thing about Physics 100 is it's also the institutional memory here, right? So the efforts that have gone into it have accumulated over time. So to give you an example of what that means, so here's the current Physics 100 team, right? And so this left column, Gary Gladding, Morten Lunsgaard, myself, we are the people who have taught Physics 100 most in recent history. And Gary, in addition to starting the physics education group here, also has been shepherding Physics 100 for 20 years and sort of overseeing it, right? And so a lot of what I'm going to talk about today actually are things that Gary and Morten have developed from even before when I got here. And then, of course, since I've got here, we've tried things for the first time last fall, right? We also have a team of graduate and undergraduate students who are engaged in helping us understand the impacts of what's going on in this course. And so they're engaged in research in different aspects. Okay, so the outline is this. Physics 100 is our main focus. We want to share the activities, policies, and infrastructure that we build into Physics 100, and we have a lot of ideas of what we've been doing. We want to share some research findings on what's been successful in Physics 100 and what challenges students face. And sort of, we're sharing our everything but the kitchen sink approach. So we're going to tell you a little bit about a lot of things we're doing. Okay. Okay, yes, I see that there are questions popping up. So let me try to read them quickly. And would that placement test be available for us to check out? Yeah, if you send me an email, I can send you a copy of it. How do they proctor the placement test? We've tried placement on math prereq, but it is online and not proctored. So we get students cheating their way into a class they're not prepared for. Does Physics 100 put them? Okay, that is a good question. How are they proctored? You know, I don't know how they are proctored. Yeah, I don't know the answer to that, sorry. But does it put them behind for finishing the degree? No, because the on-sequence time to take Physics 211 is in the spring. And so there is that fall semester where students are taking other classes before they take Physics 1. So Physics 100 is one of those classes. Okay. Thanks. Okay, this is a warning slide. Of course, there's no one-size-fits-all solution. I'm going to tell you about what we're trying at the University of Illinois. This is a large, public, predominantly white, four-year research university. Kanem and Sid, they warn us that physics education research specifically oversamples exactly from institutions like this. But even if you're at an institute where you would say, this is a large, public, predominantly white, four-year research university, it turns out the local context matters a lot, right? And trying to understand what your local context is and what will make sense in it is sort of what we spend a lot of time thinking about. And so, of course, I think it doesn't make sense to say, oh, they're doing this at Illinois, let's do it here. But hopefully the way that this can be helpful is we can tell you what challenges we thought about, what solutions we thought about implementing, and why we thought that would work. And maybe that can spark some design thinking for your local institution. Okay, so here's the outline. We got to the outline on slide 12. We're going to tell you about the overall course design of Physics 100, just in brief. The main things we want to tell you, though, are some of these things that we think are really novel to our approach. So how do we try to, say, emphasize learning over evaluation? How do we encourage the building of social connections between students? How do we use learning assistants who are undergrads who have taken this Physics 100, Physics 211 course sequence, and now they're coming back to be undergrad TAs in the discussion section? How do we incorporate them? And also, how do we use them to inject advice from past physics students into our course? And then finally, Muxin is going to tell us about Challenges for student collaboration. So Muxin's been very involved in doing research in our discussion sections to try to understand what's going on when students collaborate and what sorts of things do we need to do better at, and what sorts of things do we need to try to improve in our discussion sections. Okay, so number one, course design, I'm going to go very quickly. So Physics 100, it's a 2-credit-hour course. So it's 1 hour of lecture a week, 1 hour of discussion a week. This is half of what is there in Physics 211. We take an overall active learning approach. And so we have a large lecture that is 150, 200 people, but we use iClicker, so they answer multiple choice questions. They discuss together with people around them in the lecture hall. They watch a video pre-lecture and answer questions before the lecture. And so they get some exposure to the material. So we spend a lot of the lecture having them use what they learned already to answer questions, try to figure out how those ideas work. And in the discussion section, we have group problem solving and worksheet activities for them to work on. And the content is the first 4 weeks of Physics 211. And so here are the lists of topics. So it covers kinematics and dynamics and circular motion, universal gravity. We have a couple of weeks also for review just to help students go back and consolidate things that they learned about. And the idea is to present some of the topics that people might have seen if they take a high school physics course and be very familiar in. Kinematics and dynamics, these are sort of foundational. But at the same time, we're injecting space to do things like teaching students about vectors in week 4, teaching students general ideas about physics problem solving that we're injecting throughout the course, right? And so we're not trying to cover all the content. We're trying to cover some of the content and some general physics learning strategies and things like that. Okay, but I'm not going to talk about this. I'm not going to talk about active learning. There are lots of resources to learn about active learning. What I want to talk about is how we emphasize learning over evaluation. And so we have 3 things that we do. We do something called mastery-based homework. We use more frequent lower stakes assessments, and we give improvement bonus points. And I'll talk about all of these. So what's the mastery-based homework? And so let me tell you about a traditional, typical, idealized homework cycle. So students get some problems. They submit them before the due date. After the due date, they get their grade. And then they can see the solutions. They can go back, see what they got wrong, check the solutions, learn from the solutions, and then maybe even do new practice problems that'll prepare them for the exam, right? Of course, this is highly idealized. You can see that a lot of what's being incentivized here is this initial attempt on the homework problems before the due date. So the way that the mastery homework works is that you get multiple attempts before the due date. Right? And so what happens is you start in something called version A. So it's one version of the homework problems. And for us, it's between 4 to 6 problems, and you can submit them because the homework is done on an online computer system. So if you get 100%, you can sort of leave this whole cycle. You've mastered version A, and you're done with the assignment, you get 100%. But if you don't get 100%, if you get 1 or more questions wrong, you have access to video solutions. And so these are brief solutions where people can see how to solve these questions, right? And so if you didn't master it, you can see the solutions. And then when you click next, you actually get a new version, version B of the problems, right? So you can try again. You get another attempt to get 100%, and that'll be your grade. And you can be done with this homework section if you get that. But again, you might get some wrong. And so there's solutions again, right? And so there's a cycle of attempting some problems, getting feedback, and trying again if you didn't master it. Okay, and so your grade on the mastery homework, it's either 100% if you got 100% on any of these 4 versions, or it's your highest try of the 4 tries. Okay, so what are the target benefits? Why do we even do this? So instead of scoring students' first attempt, we're providing opportunities to learn, and we're rewarding learning on homework, right? I think we often tell students that we're incentivizing your learning, right? We tell students that after you get the homework grade back, you should go back and do your studying on your own. But we're actually building in the structure so that students can do this during the homework, and they actually get rewarded in terms of their homework grade if they are able to learn from that mastery sequence. Research on this in Physics 100 shows that the mastery homework produces better learning over standard problem types. And so that's a study that's directly done by Gutman and others in Physics 100. Okay, so we want to do this same idea of giving students more frequent opportunities for feedback in the assessments also. And so in the typical intro courses, so Physics 211, that's Physics 1, there are 3 midterms and a final. And the first midterm actually happens around week 5 or week 6. So it's pretty deep into the 15-week semester here. So by contrast, in Physics 100, we do a quests plus exams model. And so the midterm exams are 2-hour exams. The final exam is a 3-hour exam. What we do is instead of offering 3 2-hour midterms, we instead do these 1-hour quests, which are shorter assessments, and we do them earlier and more frequently. And so the first quest happens at the end of week 2. And so the idea is just earlier and more frequent feedback about study success, give students more time to adjust their study strategies, more opportunities to revise their study strategies if they don't pan out. And so in Physics 211, this often happens where students don't do well on the first midterm, but it's pretty late in the semester already, and they only have a couple more assignments to go to test out new strategies. So by having more assessments, we hope to give students more chances to get feedback on revisions to study strategies. Of course, quests are also worth less. They're worth 6% of your grade versus 10 or 15% of your grade for the midterms. And so initial struggles have a smaller impact on your course grade. We also have an optional quest, which I didn't talk about in the previous slide, where optional quest 6, you can drop your lowest quest grade, and it happens later on in the course, right? And so that's for students who maybe don't do well in the first couple of quests, quest 1, 2, or 3, but maybe by the end, you've sort of figured out how to study, you've learned more physics, and so you can take this quest at the end that will replace a low quest grade that you got earlier. Okay, finally, we also offer improvement bonus points. So of course, with these assessments, especially Quest 1, Quest 2, and the midterm, we have a discussion where we explicitly want students to recognize what they've learned, but also recognize what they'll try to do to improve. And so this is a little bit of trying to positively frame what you've done. And so a lot of times students on Quest 1, they don't get the grade they want. Maybe they get a 50%. And in a lot of venues, that's a failing grade. We try explicitly to get people to recognize that that actually means you could have learned a lot. So reflect on, before you took this class, if you had taken this quest, what percentage would you have gotten, right? And so most people recognize they've improved already over that. And so, maybe you would have gotten a 0. So 50% means you actually learned 50% of everything you had to learn, right? Which is, it's something, it's not nothing, it's maybe not your goal, right? And so we're also trying to come up with strategies for how we're going to change our study strategies to learn that remaining 50% as we go on, right? But of course, getting a bad grade initially, it can disincentivize this, right? Because if you bomb these first 4 quests, it's really hard just numerically to come back and get an A in the course, right? And so actually in the midterm, we offer what we call midterm improvement bonus points. If your midterm percentage is higher than your Quest 1 through 4 average, we add bonus points proportional to improvement, right? So essentially what we're doing is we're weighting your later grades in the course if they show a lot of improvement more so that it can boost your grade. We do the same thing in the final exam, okay? And so the reason why we do this is so that students' course grade is not limited by initial struggles, right? We're trying explicitly to recognize, especially those first exams you take in college, maybe, can be bumpy and can give you feedback that your study strategies that you bring in from high school aren't going to work. And so what do you need to change? We also want to reward students who show improvement, right? If you get an A on the final, right? I think that means you're well prepared for Physics 211. And so we want students to feel like their Physics 100 experience is that A that they got at the end and not necessarily what happened in the opening weeks. Right, and it explicitly incentivizes continual improvement up until the end of the course. Okay, sorry, I see questions. What e-learning platform do you use? Oh yeah, we use a platform called Smart Physics, which was actually developed here at the University of Illinois, and it's published by Macmillan, I think. I assume the solutions will if not already, be readily available online. This entices students to not spend time trying to solve the problems. I found that many students simply cannot risk using available solutions. Yeah, I mean, there's many things that happen in the homework, I think, to disincentivize copying. So one is, I think that the mastery homework gives people sufficient opportunity to do well. And so many students will just go through it, recognizing that the solutions to the problems are in the homework if they complete it. There's also some randomization that happens in terms of the version and the numbers, so you can't just copy numbers exactly. Could you elaborate how you grade the homework? Yeah, so for the mastery homework, how we grade it is just on the 4 tries that you have, what's the highest score that you got, right? And how much percentage in the homework is in the total grade? Yeah, I think the homework is 15% of the grade. Oh, suddenly I don't know, but it's around 15%. Okay, thanks. Okay, we also try to explicitly build social connections between students in terms of finding homework collaborators. We also have an explicit discussion about transitioning to college. So for finding homework collaborators, we do things in the lecture. So in the lecture, students are always discussing with their neighbors, but they may never actually learn their neighbors' names or anything about them. And so we explicitly, in the first weeks of lecture, we have times for students to just meet your neighbors, talk to them, learn about them, see what you have in common. We also have explicit times and explicit slides in the lecture where we tell students you should exchange contact info with 5 people around you, and you should contact them to find time to do homework together, right? Because oftentimes students want to do homework, but they don't have anybody to contact. So we want to ensure that this is happening. In later lectures, we actually check in with them. Did you actually do this? And if not, maybe you didn't get anyone's contact info. So we do the contact info exchange again. So we do this for the first couple of weeks. There's also a Piazza message board where there's a Find Study Partners function that people use. And it seems like it's successful for some small subset of students. We also reframe the office hours as a homework study space, right? And so instead of just coming to office hours if you have a question, or a lot of times the freshmen who are coming in don't even know what office hours are, we frame it explicitly as just come and do the homework, and you can work on the homework. You can ask the TA or the instructor questions. You can work with other people. So this is a picture of what our office hours looks like. It just looks like people working on the homework together. Okay, so obviously we want to build opportunities for students to collaborate. We know from research in physics education that social connections predict their course performance. So trying to enhance social connections seems helpful. Social interactions, we believe, can also help normalize the challenges of physics class. A lot of times students who work alone, we hear they think that, oh, something is weird because they're really struggling on the homework, right? But when you work in a group with other people on the homework, you find, oh, the homework is just challenging. We also hope to create social groups that can persist into Physics 211. Okay, we also do a week 1 discussion about the transition to college. And this is taken from a short activity to normalize academic personal concerns in the transition to college. So there was this research study published by Kevin Binning et al. Where they did an activity like this, and we take the activity exactly from them because we think it aligns with what we're trying to do. So to give you an idea of what happens, there's a short presentation where myself or a TA in the discussion will present just generally about all the things that could be challenging when you start college. Then we give students a 10-minute writing exercise. What concerns do you have about college? We share quotes from upperclassmen where they share concerns, but also how they changed and went away over time. And then we have students talk with each other and share and discuss their concerns. So the finding from the Binning et al. Study was that this activity plus a follow-up, so just two class periods, improved the average course grade for female students and non-white students in engineering physics. Okay, so that would be great. I think the reason why we are comfortable doing this in our class is it also aligns explicitly with all the other things we're trying to do, explicitly in terms of connecting students. Just to give you an idea of the kinds of concerns that come up, here's a sampling of what students wrote about in the writing exercise. Some are what you would expect, some are maybe what you don't expect. So they, of course, write about academic concerns like a change in school environment. For example, I took AP and stuff like that in high school, but it's not the same as a college course. The way I did homework or studied isn't the same as I have to do it now. Students also write about self-efficacy. So one student wrote, a concern I have about beginning college is that I'm not smart enough to be here. They also have concerns about organization. It's been difficult for me to organize all my classes and meetings and deadlines. Of course, students have a lot going on. There's a lot of course logistics and things just to keep track of. But students also express social concerns to us. So they'll say, making friends is a concern. I was and still am a bit worried about if I will make friends in college. Coming to college, I definitely have worries I won't make friends. There's also a change in the living environment. My main concern is adjusting to college life, as in being away from my parents. There's also work-life balance concerns. So in terms of organization and discipline, one student said, one thing I'm concerned about while entering college is having the self-discipline to manage my academic and social lives responsibly. Valid. Also thinking about jobs. So if you would start working part-time, would balancing a job and school be too strenuous, right? And so some of these things are directly related to, say, learning physics, but other things are just general things that are about transitioning to college, right? And so our goal is, in having this conversation, is to help destigmatize these concerns, to help students build early connections with their peers, and sort of around these concerns also to try to normalize them. And to also start a class culture of acknowledging struggle and concerns. Part of Physics 100 is recognizing that this transition to college physics is hard. Okay. Okay, so learning assistants. So we did not create learning assistants. So this started out of the University of Colorado at Boulder. These are undergrad students who take a course and then come back and act as undergrad TAs. And so we have past students who have been successful in Physics 100 and 211. They come back and teach discussion sections with a grad TA. They also take a physics teaching pedagogy course. And the research on learning assistants is that there are many examples of them decreasing failure rates in intro-STEM courses. So this is all good. So what have we tried to do with learning assistants that we don't see other people doing? And so we try to inject some of the wisdom of these learning assistants back into the course. And so we explicitly try to find ways to share tips from past physics students. So in week 2 of the course, we have learning students provide their tips to success in physics courses, both Physics 100 and Physics 211. And I share these in lecture. In week 12, we actually have a learning assistant panel in lecture to answer students' questions about Physics 211 and being an engineering student here more generally. And students have a lot of questions, it turns out, about this. So I'm just going to give you some ideas of what gets shared in the week 2. And so here's one of the slides that gets presented in lecture. And so the learning assistants come up with this list, and some of the advice they come up with are like things they had to learn about solving physics problems. So for instance, they say, draw the picture, just draw it, even if you think you memorize that kind of problem. Or they say, you can look at a problem and it can be overwhelming. If you're lost on a problem, just go back to the equations you know. Okay. But some of what learning assistants have to say just have in general to do with the experience of being in Physics 100 or 211 and sort of their experience during and also their advice for how to frame it. And so they also say, in Physics 100, I thought I was behind everyone else, but by the end I was ready for college physics, right? And so there's sort of a success story, even if you feel like you're behind. Even if you know physics or if you don't, Physics 100 is a really good intro to how physics courses work at U of I. So you'll have more confidence in the start of Physics 211. So you might even be a leader in your 211 discussions, and it sets a foundation for topics that gets harder. Okay. And then the last one, don't go into it saying I'm not a physics person. A lot of people do that, and you're setting yourself up for failure. There's no such thing as a physics person. Instead, you should think this is a new skill I'm learning. It's a new way of thinking. With Physics 100, you're getting a foundation for it, and it's really not as hard as you think it is. Okay. So some of our goals, especially with trying to get the learning assistant's perspective on being a student in these courses, is we not only have learning assistants act as teachers and role models for beginning engineering students, we also have them providing advice from peers about learning strategies, framing your experience in physics, and also your physics learning mindset. And we think it's also normalizing some of the initial worry, but also normalizing eventual success coming out of Physics 100. Okay, I see there are some questions, but just to make sure that we have enough time to get to the end, I'm going to go on to this fifth part. And so Muxin has been doing a lot of research in terms of video observations of the discussion sections. And she's going to talk about some of the initial findings that we're thinking a lot about right now. So Muxin, please go ahead.
So I want to talk through two moments that I think are good examples of some of the things that we've been learning. So one is, so we collected these video data in fall 2020. They're on Zoom. Can you go to the next slide? Mm-hmm. So the first moment, students are talking about this Newton's second law problem where a block is hanged by two strings and they're asked to compare the tension on the left string and the right string. And the canonical solution to this problem is to see how the forces in the x direction will cancel out. So they would write equation like TL cosine 30 equals TR cosine 60, and TR would be bigger because cosine 60 is smaller. So in this moment, we have 4 students, and before this clip, student A, B, and C sort of reached a consensus that the tensions should be equal, which is not correct. But here we see student D jumped in at this part of the conversation and said, would that mean that one of them would have to have like less tension because the x components need to cancel each other out, which is sort of the more correct way of approaching it. And we see student B sort of reacting to D in a way, but actually sort of proposing a new idea, saying that, oh, they have to cancel out the weight, don't they? And then student C say, oh, because like it's talking about the tension of the strings overall, not just a vertical and like horizontal components, which is proposing another new idea and not necessarily responding to what D was talking about initially. And C here also is disengaging a little bit, saying, oh, just do what you say. Like, I'm too brain dead to think about this right now. I need the math. And A also is sort of delaying the discussion in a way, saying, well, we're about to find out. And then student D continued to offer more explanation to sort of get their group members' attention, saying that, oh, like if their x components need to equal to each other, but the x is equal to like the tension times like the cosine of their angles. So then the cosine of one of the angles is going to be less. So then the tension would be greater to compensate, which is a really great explanation. And we see student A saying, oh, let's just try figuring it out and not taking up D's idea. And can you next? Oh. So D continued on this line of reasoning and offered a correct explanation. But after that, we see C saying, oh, it's hard for me to think that way. I think mostly through the math part of it. And D says, this is math. And C says, I mean, like pure numbers. I like pure numbers. Pure numbers make sense. And D sort of ended with sort of awkwardly saying, oh, I don't know how to explain this. So in this clip, we see how student D made several attempts to share their approach to the problem, but the group didn't take on their idea. They struggled to sort of listen and respond to each other's ideas, which led to an unsatisfying ending of the discussion of this problem. And I think this clip also sort of shows that we often have a simplistic model of collaboration, thinking that, if we put students together, knowledgeable students can share the correct answer with others. But here we see that it's sort of more complicated than that, and students can make moves that show like their resistance to taking up another student's ideas. And in this process, there are also a lot of like social emotional risks involved of like being wrong and being challenged. And we also see student D express a lot of frustration of like not being heard. So the next moment that I want to share is sort of a different kind of conversation. It's the same group of students, and they spontaneously had a conversation about their experience in engineering. And it sort of started with student B discussing their friend's experience in engineering, saying that she just feels like everybody around her is so much smarter than her. So it's like it's bad for her self-esteem. And C says, oh yeah, that kind of sucks. D says, I feel like the story for everybody in engineering is that we all like hate our lives. Yeah, nobody is having fun here. No. And I feel like everybody kind of has that feeling too. Like I definitely have felt at times where it's like, damn, everybody here is so much smarter than me. And A jumped in and said, oh yeah, that's how I feel when I'm with you guys. And C said, I mean, like, you just need some time to remember, like, for like me, I may sound like I know what I'm doing, but trust me, in my head, all of that shit is fucked up. It never works out like as good as you think it may be for other people. Everyone is struggling. Everyone is. Isn't that called imposter syndrome? Something like that? I think so. I think that's what it's called. I think remember talking about that at the beginning of the semester, actually, we were learning about it. So this is a really interesting moment that we found in their discussion that was like not necessarily about physics, but we see that they were able to share their struggles as engineering students. And in some way, this kind of conversation normalized the feeling that everyone else is so much smarter than me. So from these videos, some of the future goals for designing collaboration, one is to offer explicit support in like helping students to think about each other's ideas, to listen to each other's reasoning. And we also want to create opportunities for students to discuss their shared experiences, like the second clip. And let's see, so some of the first areas for redesigning or thinking, one is to better train our TA and LAs, and another is to maybe create a different discussion problem or task that can actually help students in like understanding each other's idea. So yeah, that's it.
Okay, thanks. Great. Yeah, so this is the outline of topics that we covered. We talked about the overall course design of Physics 100, how we've tried to change the policies and structure of the course to emphasize learning over evaluation, building social connections between students, how we use learning assistants to provide advice from past physics students, and some of the challenges for student collaboration that we're working on. So just to close and summarize, I sort of want to reiterate how we're focused on course infrastructures, right? In terms of we're thinking about structured mechanisms rather than out of class support or less tangible aspects of department culture for supporting students. One of the successes of Physics 100, I think, is that it continues to exist as a course, and that has institutionalized that support that we have for students. We're trying to develop course structures and policies that align students' course experiences with what we preach, right? We preach that you're always trying to improve and get better, and now we're trying to think of course structures that actually incentivize that. Again, it's an alternative to thinking about brief activities that focus on impacting students' beliefs, but without changing the course. Okay, well, thank you for listening and your time. And I think we have time for discussion and questions.
We do indeed. Thank you so much, Eric and Rushin, for this. And there's a sort discussion question in the chat about the resources that this takes up, because it does take this type of a redesign takes up considerable under like resources in terms of grad TAs and undergrad LAs. So to sort of change the question a little, what do you think, if you have a much more modest budget or modest access to resources, what kinds of things would you say would be most vital to implement that, somebody who is not at an R1 basically could do?
Yeah, so, right, I think, finding undergrads who are interested in teaching is one way you can do it. If you have a hard time getting money or getting interest in that, that can be hard. I think what we talked about in terms of getting advice from past students, that could be more of a one-time thing. Like maybe you could find some students from your class from before that you thought would give good advice to come to your class and talk with your current students, where you could meet with them for an hour and come up with a list of advice that you can share with your students later. And that's sort of how we did our list of tips from past LAs. So it may be that definitely you can't do all of the parts of this with fewer resources, but there may be specific aspects where you can find a lower cost version of getting some of those ideas into your course.
Great, thanks. And somebody asked a question regarding moving these types of reforms into subsequent classes. So they said 211, for example.
Oh yeah, that's a good question. Yeah, so I mean, you can see already the enormous effort that goes into changing the course and sustaining these changes. One reason why Physics 100 has been successful at staying constant, I think, is Gary Gladding being around and sort of overseeing the course. Whereas Physics 211, it's an even bigger course with even more logistics, but also where instructors come in and out. And so I think figuring out how to institutionalize changes like this into 211 is a larger task that requires more buy-in and energy from the department beyond just our Physics 100 team. But I think we definitely want to make it happen, because a lot of the constraints we feel is that we want Physics 100 to support 211. We also want Physics 100 to be the best learning experience, but sometimes those things might clash, because maybe we want to change how assessments are done in Physics 211 so that we can also change how assessments are done in Physics 100. So yeah, so there's definitely some desire to change 211 to try to align these things better.
And could you briefly describe the training and professional development that the learning assistants receive?
Oh, sure. So we model it based on the materials from the Learning Assistant Alliance. I forget what the acronym is, but it's LASSO. And so there are readings that students do about teaching and pedagogy and cognition and education and things like that. And they'll come into the pedagogy course and they will discuss some of those ideas, try to connect it to the teaching context that they're in. And we might even explicitly talk about some of the specific ways that it might connect with Physics 100 specifically for Physics 100 LAs. Yeah, but if you're interested in those materials, I think we're just adapting the publicly available learning assistant materials.
And so I also have a question for Mushin, like about the different types of interactions that were featured in the research. Do you know sort of what can we do to set up things so we can have positive group exchanges, things like that? Do you have any suggestions?
I think so. One thing that we've been thinking a lot about is, so we also have some recorded like TA and student interactions, and we see that normally the TA would focus a lot on like explaining the problem or the correct answer than actually acting more like a facilitator for the group to like encourage each group member to share their ideas, whether they're correct or not, and to kind of help with this overall like dynamic in terms of like encouraging them to listen to each other and like talk about their ideas. So like I think one thing we're trying to do is to in some way incorporate that into the training of the TA and LAs, so that when they are helping the groups, they're sort of like creating the norm of like, oh, this is a space for us to actually take each other's ideas seriously and to hear like voices from different group members.
Great, thanks. And let's see, do we have any more questions? Because I think we have time for maybe one more.
Yeah, I see Alma's comment. I think that's a great idea of finding a structure in other places to try to do some of this work. We also have first year experience courses. I think it's called Engineering 100 here. And so a little bit about why we're thinking about what we are in Physics 100 is we also, like, even if students learn about things like imposter syndrome from these first year experiences, we think that actually connecting it to the context of their courses, like talking about these same ideas again in the courses, helps build a connection, where otherwise it might just feel like, oh, we talked about it and now we're in the physics course.
So we have a question then. Piazza works for a small subset. Can you elaborate?
Oh yeah, just because I know that there are 400 students in the course and the number of people who message in the Piazza Find a Study group is less than 400. It's probably closer to 30 to 50. So that's why we try lots of different avenues of getting students connected with each other. Because I think there is a social barrier to doing it. We're also not requiring students to do it. And so people may not want to do it for lots of different reasons.
Cool. And then somebody wants to know about how is homework graded and how many students typically take Physics 100? Oh
yeah, so our homework is all through our online homework system, which is the Smart Physics system that I mentioned earlier. So it's graded automatically. That's what makes the mastery homework possible, is because we can pre-design all of those activities and they can be sequenced out by the system and be graded automatically by the system in real time. How many students take? About 400, although it fluctuates. For each cycle, you have a higher difficulty level. Sorry, I see a question about the mastery homework. So in what I showed, that would be like for one set of ideas. So it might be for velocity versus time graphs and reading it, right? And so every version would be questions about that. But then once you get through that, there might be another set of 4 mastery versions that are about a different topic, right? And in general, the topics get harder as you go through. So multiple mastery cycles per homework. Is Smart Physics free? No, students purchase it. It's sold by a publisher. Yeah.
Cool. And so I have one last question for you both. What do you think your next directions are for this work?
That's a great question. I think, what Muxin mentioned about things that we would think about in the discussion, I think now that we've collected a lot of data about what happens in discussion, that's one area where obviously we want to focus. I think we are also continually focusing on how to understand the impacts of all of these changes that we're making. And it's hard because we keep changing a lot of things all at once. And so, one thing that we think might be useful is just interviewing students about how they perceive all of these different facets of the course. especially since a lot of the impact we're trying to have is on students' perceptions of what it feels like to learn physics.
Cool. If there's nothing else people want to add, I will stick around for a little bit afterwards, but we will stop the recording. Thank you everybody for attending. Thank you, Eric and Muxin, for doing this for us.